This presentation is on optimization over a geometric fabric. At a high level, it's about encoding nominal behavior in such a way that we can optimize over the top of it by pushing it away from its nominal trajectories to optimize a potential. And I'll talk about how that fits within the context of what we call Riemannian motion policies for behavioral design. This is work done at NVIDIA in NVIDIA's Seattle Robotics lab. At a high level, SRL works on collaborative robotics, from perception to deep learning to behavior generation, all about trying to perceive the world in real time and react to it in real time so we can accommodate the inherent uncertainty and dynamics of problems like these. Okay, so an example of this sort of system is what we have here. Here we have Yumi just playing a game of trying to keep drawers closed. I'm constantly opening them, just playing with them and creating a dynamic and uncertain environment, and Yumi's role is to just adapt to that constantly. What we did to design that system was develop something called Riemannian motion policies, or RMPs. And the high-level idea of that is to design behavior in an intuitive way, create a tool set to enable people to very easily and flexibly design behavior modularly. So key to that is designing behavior in parts on many different task spaces simultaneously. So task spaces might be spaces of points on the robot's arm, just mapped from the configuration space using forward kinematics. Or might be distances between those points and points in the environment. Or it might be something even more abstract, but on each one of these spaces we can put what's called an RMP on that space, which is a combination of an acceleration policy, how to accelerate from any point and velocity, position and velocity, and a corresponding priority matrix that might change through the space as a function of position and velocity. The priority matrix tells us what directions the policy cares about the most at any given moment in time. And by doing this, we give designers a very flexible tool set for designing behaviors and sharing them among different robots. Here's just an example of us using it also on the Baxter robot. Basically using Riemannian motion policies, we can instantaneously get very fast collision-free behavior. In this case, we use no planning, just Riemannian motion policies and some very simple heuristics. So these tools are very powerful and flexible, but they're also, in a sense, somewhat unsafe if you don't have the expertise, if you don't have experience with it. It takes some expertise to get the behavior that you see in these examples. Just kind of characterize this. If this is the class of RMPs, the total class of RMPs, the set of stable RMPs might be considered here. Because I have intuition for this and I have experience with it, I'm able to kind of like work with this set. So a lot of them are within the stable class. Some of them are in the unstable region, dangerous region, but I can pull them into the stable region pretty easily because I have experience. But in trying to get these to unexperienced users who want safer tools but want the flexibility and the power of this tool set, we need to really analyze that class of stable RMPs. So a lot of the theoretical work we've been doing has been in trying to characterize what are the set of stable RMPs. I would characterize what we've looked into so far as actually being relatively small. We've done some previous publications on things called geometric dynamical systems or Lagrangian dynamical systems, which describe RMPs as a type of non-classical physical model. But they have a particular issue, which I'll talk about in just a little bit. The main content of this talk is trying to grow beyond that. And what we have now is what we call geometric fabrics, which I think capture a much broader class of stable RMPs and capture a lot of the intuition that I've had in the past in designing these for specific demos and stuff. So we'll go into that in more detail. But first, let's take a quick look at our earlier attempts and what their limitations actually are. These geometric dynamical systems, or what we now know as kind of a broader class of Lagrangian dynamical systems, are basically RMPs defined by the Euler-Lagrange equation. We start with the Lagrangian, we apply the Euler-Lagrange equation, and we get an equation of the form that's shown in the middle here, which is a typical mechanical system, non-classical mechanical system, but it has the form of an RMP. And it's really characterizing behavior as a dynamical system. It's a good start. It generalizes what we might call geometric control, but it has a particular limitation in that this metric, this M sub L, plays two roles. We want it to play the role of a priority, because in RMPs, policies are combined with a priority, and that ends up being an important part of how to combine them in a way so they don't fight. But it also, in this context, has to play the role of designing part of the behavior itself, so designing part of the policy. So in this case, it's both for behavior design and priority. In many cases, we don't have enough flexibility in that metric for it to play that dual role. As an example, some of the work that we did once we started understanding these Lagrangian dynamical systems is in learning Riemannian metrics. And here are two examples of these things, two publications we recently put out. I won't go into detail about these, but the high level is we can take a dynamical system and stretch the space so that the behavior of that dynamical system matches human demonstrations. These two examples give two different ways of doing that, but basically it's learning Riemannian metric to represent that stretching. But in all of these cases, this metric is designed and learned solely to represent the behavior. It doesn't capture the notion of priority that's necessary to combine them with other RMPs. So once we came to put them in RMP trees, they started conflicting sometimes and fighting with some of the other RMPs, especially collision avoidance RMPs and stuff. So that brings us to optimization fabrics, our most recent tool set for a theoretically founded tool set for designing RMPs. And at a high level, we can think of an optimization fabric as an unbiased nominal behavior that we can push away from to optimize a potential. Kind of to decompose that, we have a nominal behavior, which we can think of as a set of paths that we want to follow. It's unbiased, as in it doesn't innately push the system if it comes to a rest, which means we can force it and optimize. Pictorially, this means if we place a potential in the space, rather than following specifically the nominal behavior, it's going to bend away from that, and bend away from it in such a way that it comes to rest at the minimum of the potential. So that's a general characterization of what we're calling optimization fabrics, and really just necessary conditions on what is an optimization fabric. To make this practical, we need to give some sufficient conditions on how to design these things, and that brings us to what we call geometric fabrics, where in geometric fabrics, the nominal behavior is designed as a geometry of paths, which we'll see in just a second. First, a simple example from classical mechanical systems. A classical mechanical system is one, again, defined by the Euler-Lagrange equation. That's the typical kinetic energy minus potential energy from classical mechanics. That defines a set of equations of motion that, when damped, will reduce total energy being kinetic energy plus potential energy, reduce total energy at a particular well-defined rate. And it's that energy reduction that captures the property of what allows us to optimize. This thing will form what we call a Riemannian geometric fabric, and we can look at the different components to see what we mean by that. So the nominal behavior in this case is just the classical mechanical system without the damping and without the potential, just with the kinetic energy driving it. It's unbiased because intuitively you can think of it as if a classical mechanical system comes to rest, it'll remain at rest. And it optimizes because if you analyze this total energy and how it reduces, we can see that it comes to, it drives itself to a local minimum of that potential. But in particular, it's also geometric in the sense that if you start at a given point and shoot off in a given direction without having a potential or damper, independent of how fast you shoot it off, what speed you shoot it off at, if it's always moving in the same direction, it will always follow the same path. And that's kind of the fundamentals of geometric mechanics. Geometric mechanics say that classical mechanical systems are really Riemannian geometries. And we'll see how that generalizes in a way that we can capture in geometric fabrics. Okay, so geometric fabrics really take that intuition and capture the best parts of it, but more generically. So for starters, this notion of geometric consistency can be described just as a geometry generator, which we have here. Geometry generator is just an equation of this form. As long as that phi is what we call homogeneous of degree 2, which means that if you scale the velocity, it just ends up scaling the outputs by the scalar squared, then we end up with this geometric consistency property. So if we start off with a single solution right here, where we start at a given point, shoot it off at a given velocity, which is shown in purple, maybe it follows this, this green line or green curve. If we start at the same point and shoot it off at different speeds, but in the same direction, the system will always follow that same path. And that's comes entirely from the homogeneity of phi. And so these geometric generators entirely capture this notion of geometric consistency that we saw in classical mechanics. But importantly, these geometry generators are acceleration policies. They're policies that define how to accelerate for any position and velocity. So we can place them in RMP trees and do all of the same things we did with RMPs, combine them and make them into metric weighted averages and stuff, and we get this well-formulated policy in the end. Importantly, if the metrics are defined by what we call Finsler energies, which we'll talk about in just a second, we can show that these metric weighted averages of geometries always themselves end up being geometries in the end. So a metric weighted average of geometries itself ends up being a geometry, which is a nice consistency property. And importantly, we can take these geometries, force them by using the gradient for potential, and we're guaranteed to optimize. So here's some examples of this. Across the top, we see one type of geometry. Across the bottom, we see a slightly different type of geometry. From left to right, we see first the nonlinear geometry itself, and then two versions of attraction to points, optimizing a particular type of attractor potential. The top geometry is just a very simple geometry that pushes away from the obstacle. And the bottom one is the same sort of thing, but switching smoothly to a Euclidean geometry once we start passing the obstacle. And we can see how that difference in geometry affects the behavior of the system. On the top, the system still cares about the obstacle even when it passes the obstacle, but on the bottom, it basically forgets it. Once it's passed the obstacle, it forgets it and just moves at with a Euclidean metric. And this just is a set of very preliminary results currently that show the flexibility and ease with which you can design geometries and use them for task optimization. Okay, so just briefly, I want to go into a little bit of how it works. I don't want to go into details of this because there's a lot to it, but I just want to give a flavor for it. To start off with, Riemannian geometry is just a special case of what we call Finsler geometry. And the key there is that all the properties that we care about for Riemannian geometry, including the representation of an energy, the creation of a metric associated with it, and the conservation of a particular type of energy, in this case called Finsler energy, are all captured in this Finsler geometry. And it's that energy that really allows us to prove optimization on these things. So that gives us a form of Finsler fabric of which the classical mechanical Riemannian geometric fabric is a part of. But we don't have to be fixed to these Finsler geometries. It turns out that we can get the same sort of energy conservation from an arbitrary geometry just by speeding it up or slowing down. So if you remember, geometries are independent of speed. If you, they just define paths that you can move at any velocity profile along. So for any geometry, we can speed it up or slow it down in just the right way to conserve a Finsler energy. And that conservation, once we've what we call energized the system to conserve that the Finsler energy, that conservation is what allows us to optimize over the top of it. In the same way as we're able to optimize over Finsler energies and classical mechanical systems because they're conserving a notion of energy. And that gives us what we call geometric fabrics. We basically start with an arbitrary geometry, take an arbitrary energy, energize the geometry with that, and we end up with a geometric fabric. And that energization transform, by getting it to conserve that energy, that defines the way in which forces are able to push away from those nominal behaviors by defining a metric associated with the geometry. So to relate this back to RMPs, these geometric fabrics are a type of RMP. They have associated metrics that come from the Finsler energy. The geometry itself is an acceleration policy, and we can place them in transform trees in the same way, pull them back to the root, combine them, and we get we get a combined policy in the end. The key idea behind geometric fabrics is that they're designed to capture a common nominal behavior that appears in many different contexts, many different tasks that we might want to solve. An example is obstacle avoidance. Many different tasks still want to do obstacle avoidance, even when they're trying to do the same different individual things. And so the idea is to try to put as much of the behavior as we can into this shared geometric fabric by designing parts of it in different spaces within a transform tree and pulling them back and using that single geometric fabric to solve many problems, each of these problems being represented by their own individual potential function, which will force away from that nominal behavior to solve the specifics of the tasks. Okay, and that's all I wanted to say here. Here's just a small list of the collaborators that we have at NVIDIA. Hopefully you can pause this to see it in a little bit more detail, but I want to move on actually to some videos that I'll just let play out to the end. This is a system that we set up for a recent demo we did in China for GTC. In China, GTC is the NVIDIA GPU Technology Conference. And just shows kind of a combined system that both combines the behavior generation tools and perception to do some manipulation tasks with blocks. I want to emphasize here that these are still RMPs. We're using the original framework to design these things by hand, but the goal of optimization fabrics, and specifically geometric fabrics, is to make some of these tools more accessible to people who have less experience with them, to make them safer to use but equally powerful as the tools that we use here. And in particular, we want to make a stable framework that we're also able to learn on top of. So during the training, we can move through a series of stable policies rather than going into unstable regions, just for a safer, easier, and more data efficient learning. Okay, and with that, I'll just let these play out to the end.